Okay guys, I'm going to do a short video on the GCSE Chemistry moles calculations for Unit 2, which is what you normally do in Year 12. So in the second half of this topic, you'll have already done solution calculations where you did your titrations. The second part of this topic involves gas calculations, so obviously involving gases. Now these should be a little bit more straightforward than the titration calculations, and students would generally find that. So what I'll do is I'll talk you through the sort of the background to it, and then I'll do a few worked examples, and then there are some questions in your textbooks, in your class notes on, I think, pages 21 and pages 22 in your books, so you can do just write that down there, pages 21 to 22. There's some questions in there which you can do whenever I'm finished, and I have either fireflied you across the answers to those, or I can do if you ask me for them. Okay, now so far in moles calculations you have used certain formula. You have used a formula working out moles, or connecting moles to mass, to our relative formula mass or relative atomic mass. You've done moles, concentration, and volume in decimeters cubed. And in this topic here, you're going to do moles again. These will be gas moles equals volume, and that's volume of a gas, divided by what we call the gas molar volume. Now the gas molar volume tells us that is the volume of a gas, okay, of any gas, okay, sorry, the molar volume, or in other words the volume of 1 mole of any gas at, and these are the conditions you need to know, 20 degrees Celsius and 1 atmosphere, and that's of pressure. Now the molar gas volume at that is 24 decimeters cubed, or if we were to do it in cubic centimeters, 24,000 cubic centimeters. So in other words, what we're saying there is that the volume of 1 mole of any gas, okay, at 20 degrees Celsius and 1 atmosphere of pressure is 24 decimeters cubed. Now that means that this is a constant value, that is 24 decimeters cubed, or 24,000, which means we can then say that the number of moles of a gas is directly proportional to the volume. Now we couldn't say that up here because the concentration was variable for our solutions, the volume was variable, and the RFM was always variable for our various different solids that we looked at. So this is why these calculations should tend to be a little bit more straightforward. So this is a really important piece of information here, and I'm going to clear this board now, so you might want to jot some of this information down here, especially these formulas, okay, and this little bit of information here, because I'm going to apply that to the questions that I'm going to do on the next board, although this should all be in your notes. Okay, so I'm going to clear the board now. If you want to pause, jot some of these down, okay, and then I'll start with some of the questions. Okay, so we're going to use the 3 formulas that I had up here. I probably shouldn't have cleared those off. I'll sort of jot them down on the side here. I'll use N for number of moles, by the way. Okay, I've used that the whole way through, so you should be pretty familiar with that. AC is concentration, and this one down here, my V, is now volume in gases. And I'm going to substitute gas molar volume for the number 24. So that's, now we've got calculations for solids, for solutions, and for gases. Okay, and just a quick reminder that the number of moles for gases, the number of moles is directly proportional to the volume. So if we take a nice simple one to get us going, Okay, so we're just going to take a combustion equation here of propane C3H8, give us carbon dioxide, and okay, so just balance that up, it gives us 5 oxygens. So let's say the question is we've got 100 cubic centimeters of propane. Okay, and the question is what volume of oxygen do I need to react that 100 cubic centimeters of propane? Well, we go back to the moles is directly proportional to the volume, and the moles here ratio is 5 to 1. So therefore the volume ratio is 5 to 1. So if I have 100 cubic centimeters of that, in order to get it to react fully, I will need, it's as simple as that, 500 cubic centimeters of oxygen produced. Let's say they developed the question, they said, okay, well then, not really that much more difficult. What volume of carbon dioxide would be made? So this time we're going from a 1 to 3. So the volume of carbon dioxide that would be made would very simply be 300 cubic centimeters. Okay, so we're applying what's called Avogadro's law there, where we're basically saying that the number of particles in the same volume of a gas, or sorry, the same volume of a gas under the same conditions as the same number of particles. That's why we can just say that, if you remember back to all the calculations we did, we were always talking about number of moles, which is essentially number of particles. Okay, so that's a really easy one. Okay, I'll do one where I'm sort of working backwards, if you like, but again, it's not particularly difficult. So let's say the examiner said this time you want to make 600 cubic centimeters of carbon dioxide. Okay, what volume of, so let's say our oxygen is going to be in excess, so I have more of it than I need. What volume of my propane would I need to start off with? Well, again, the ratio is 3 back to 1 this time. So I take my 600, obviously divide by 3 to get it across, and that gives me 200. So I would need 200 cubic centimeters of propane if I wanted to make 600 cubic centimeters of carbon dioxide. If they asked for the same, let's say they asked for how much oxygen would you need, with the propane this time being in excess, okay, so my ratio this time is 3 up to 5, so I'm taking my 600 cubic centimeters of my carbon dioxide, okay, sorry, and I am multiplying it by 5 over 3, or dividing it by 3 and multiplying it by 5. So if I divide that by 3, that gives me 200 cubic centimeters. I multiply it by 5, gives me 1 litre, or 1000 cubic centimeters, or 1 decimeter cubed. Okay, just read the question. Sometimes they specify what units they want that to be in. Right, so those are very simple. We've done one where we're working from reactant through to product, and we've done where we're working product back to reactant. So we'll do a couple on the next page, similar sort of principle, but we'll now start to incorporate these two calculations, or these two formulas that I have on the left hand side here at the top of the screen. Okay, so let's take some zinc metal, and let's take some hydrochloric acid. And when we react that together, we get zinc chloride and we get some hydrogen gas. Okay, so we've got an excess, let's say, of the hydrochloric acid this time, and we have 3 grams of the zinc metal, and the question is, this time, what volume of hydrogen gas will I make? So to get volume of a gas, I need moles, and I need the molar gas volume. So we'll say that they've told us it's at 20 degrees Celsius and 1 atmosphere of pressure, so we know the molar gas, or the gas molar volume at that, is 24 decimeters cubed. Okay, so in order to get moles of this, okay, I can't do that directly, so, but I can do 3 over 65. Okay, I can go up here and do my mass divided by the relative atomic mass of the zinc, so that's 3 over 65 will give me moles of my zinc. So okay, so it's 0.0462. Always make sure we round up correctly, okay? So it's 462, not 461. The ratio of zinc to hydrogen is, of course, 1 to 1, okay? 1 to 1. So therefore my moles of hydrogen is the same. My volume equals moles multiplied by 24. So I'm taking that value there on the screen and multiplying it by 24. Gives me 1.11 we usually write to 3 sig fig, 1.11 decimeters cubed of hydrogen would be made. Okay, let's change it around a little bit and say this time we've got to make 3,000 cubic centimeters of hydrogen, and again we'll just say, we'll assume all of these are at 1 atmosphere at 20 degrees Celsius. Okay, so we've got to make with an excess of HCl, and the question is what mass of zinc? Okay, right, so we have got to get mass of zinc, we've got to get moles, so moles times 65 will give me the mass of the zinc. Okay, so I need to get moles. I can get moles from over here by taking my 3,000 and dividing by, now I need to be careful and remember to divide by 24,000, not by 24, because I've got cubic centimeters at the top. I got to have cubic centimeters on the bottom, of course, and that gives me 0.125 moles of that. Okay, so therefore, because we're going back to my zinc, which is 1:1 ratio, I have got 0.125 moles of that. Okay, so I multiply that by 65, mass times relative atomic mass gives me 8.125 grams of zinc would be needed in order to make 3,000 cubic centimeters of my hydrogen gas. Okay, so let's say this time, okay, just doing another couple and then it'll be over to you guys to do the questions from the notes. This time I have got an excess of zinc, and I've got, let's say, 25 cubic centimeters of 0.25 concentration moles per decimeter cubed hydrochloric acid. And my question is, what volume of hydrogen gas will I make? So again, this time I'm using the second formula where I'm doing moles equals concentration times volume, so 0.025 is the volume, 25 over 1,000 in other words. Okay, so that gives me 0.00625 moles of that. Okay, the ratio this time I need to be careful is 2 back to 1. So that is 0.03125 moles of hydrogen getting produced. I go over here to my gas calculation. Volume equals moles multiplied by 24. I've got my moles. I multiply it by 24. Okay. Give me 0.075, and this is, remember, decimeters cubed. The units are important. Okay, if it's decimeters cubed, put it on, especially in gas calculations. Okay, and that is the answer. And again, just be careful they don't ask you for the answer in cubic centimeters. If it was cubic centimeters, well then that would be 75 cubic centimeters. Okay, right. So we'll do one more then. Again, working backwards. Let's say I have 0.75 moles per decimeter cubed of that, and I've been asked to make 6,500 cubic centimeters, and my question this time is, what volume of hydrochloric acid will I need at that concentration to make this? So again, I'm using these two, the gas and the solutions formula here on the left hand side. Okay, right, so excuse me, I have 650 divided by 24,000. I got to remember to put it into 24,000 to give me moles of this, so therefore I have 0.27083 moles of that. I've got to go back, it's 2 up to 1, so I've got to multiply that up by 2 this time to give me 0.5416 moles. Okay, that's of my hydrochloric acid. I'm looking for volume of hydrochloric acid, which is moles divided by concentration. So I take that and I divide it by 0.75. Okay, equals 0.72, and remember, that's dm cubed, or that would alternatively be 720 cubic centimeters. Okay, so I think I've hopefully done one or two, one to cover kind of all eventualities that might arise at GCSE there, and anything else that does crop up in an exam question probably is a variation of the themes that I've just spoken about. Okay, as I said earlier, the questions I think I put on were page 21 and 22 of your notes. There are also ones in your textbook as well that you can have a go at, and I would encourage encourage you to do that and check them. Okay guys, hope that helps. All the best.